detectors are located inside the nuclear reactor core. We have to withstand high temperatures, high pressure, in order to operate in this harsh environment. And as conditions are pretty severe, only several types of detectors can operate in these conditions, and specifically semiconductor detectors, which has or scintillation detectors, which have a crystalline structure, can't work on this condition due to the damage of the crystalline lattice, and these detectors can't used in these experiments. That is why we basically use for monitoring the neutron fluxes gas field detectors as proportional counters or ionization chambers or some other specific detectors, which I will show you in my presentation. So let's start with detectors which are located outside the nuclear reactor core, and this detector called out-of-core detectors. They are located specifically in several places on the outer surface of the vessel, and one of the most important and most popular device is just an ionization chamber, which contains a noble gas, usually argon inside, and in order to detect neutrons, as I showed in my previous lecture, a material that can absorb neutrons is coated on the surface of the ionization chamber, and in this case, we usually coat it with boron, and these detectors are called boron line. And there is one problem that at nuclear installations, at nuclear reactors, we have, in addition to high fluxes of neutrons, we have high fluxes of gamma radiation, gamma rays as well. And in order to distinguish between them, we have to get rid of these gamma ray reactions, gamma ray current. And for these purposes, the so-called compensated ionization chamber is used, where we have actually two ionization chambers, one located inside each other, and one operates, can detect only gammas, and there are no boron coated on the inner wall. And for the second detector, you have this material. And measuring the total signal, the sum of these signals from two detectors, you can extract the flux of gammas from this and get the pure, the clean signal which contributes only to neutrons. And this approach is applied for this ionization chamber by getting out of the core. And these detectors, you can see some installation, just a picture showing there these detectors can be. This is an aerial view of the top view of the detector. You can see that the detectors can be placed here, here, here in symmetrical positions to uniformly measure neutron fluxes. And in these conditions, neutron fluxes are not so high compared to they're still high, but not so high compared to the neutrons which are appearing inside the nuclear core. And for these reasons, typical, for example, the same proportional counters, boron trifluoride detectors can be put in several positions. Here, we have a combination of ionization chambers and proportional counters to monitor and understand the whole flux of neutron outside the nuclear reactor. And this measurement of neutrons can give you the understanding in what phase of the nuclear reaction and the nuclear reactor operation mode we are. For example, for startup periods when we're only starting to get to increase power, have typical neutron fluxes located in this region is 10 to the power 4. Intermediate range when we are very close to our desired point, and the power range, which is has neutron fluxes about 10 to power of 10 neutrons per square centimeter. This is our desirable flux, and we measure it with this installation using fluxes of neutrons. And in every stage, we use different methods to measure different detectors to measure these fluxes. Top, intermediate, and power mode of operation. In core detectors, which are located inside the nuclear reactor core, there are several channels which are packed with auxiliary equipment in order to measure pressure, temperature inside the nuclear reactor core. And one of these channels is also used to measure the neutron flux. And there are two types of detectors which can be located inside the nuclear reactor core. The first of them is a fission chamber, the detector which I explained in detail in my last lecture. Yeah, this is my previous lecture. And the mechanism, as you coat the wall of your ionization chamber with some kind of material, for example, uranium-235 or plutonium-239, in order to get to fission fragments with energy of about 160 MeV, which can ionize the gas inside it. Usually they're filled with argon gas, and you can get the flux of neutron inside the nuclear reactor core. Here is the picture how this chambers look. They're pretty long, up to 4-5 meters long, in order to be and measure the flux of neutrons along the vertical axis of the nuclear reactor vessel. And as I said, conditions are pretty hard inside the nuclear reactor. We have temperature, which is about 300 degrees. We have pressure, which is about 170 atmosphere. This is for pressurized water reactor figures, and high gamma flux, and concerning neutron fluxes, they can reach the value of 5 times 10 to the power 13 neutrons per square centimeter per second. Very, very high values. That is why, if you look at, for example, fission chambers, you have an effect which is called decrease in sensitivity by the fission formulas, because your uranium-235 the amount of it starts to decrease significantly due to these high fluxes, and you have to have a mixture of, for example, plutonium-239 in order to regenerate the material inside this chamber. Let's talk about the second detector, which is used inside the nuclear reactor core. And this detector is called self-powered detector or Hubble detector. The principle of operation of this detector differs from devices which I explained to you in my previous lectures. And the structure of this detector, you can see from the name, self-powered, means that it doesn't require to apply an external electric field to the detector. And the principle is very simple. You have a material, specifically material. This is a picture how this detector looks like, and you have a material, for example, rhodium or vanadium, that have a pretty high cross section, a thermal energy region, about 100 bars, for example, for rhodium. Of course, if you compare to other sorts of detectors, for example, for helium based detectors or boron detectors, the cross section is much lower. Yeah, but as we are great inside the nuclear reactor, and we have much higher fluxes of neutrons, this cross section is enough for measuring the flux of neutrons. And the construction is simple. You have a collector and emitter, and the emitter is made of this isotope, rhodium or vanadium, and this isotope actually absorbs neutrons and it emits electrons through the beta decay channel, and these neutrons are collected on the collector, and you simply measure the current, which is induced by neutrons. And this current, the value of this current is proportional to the neutron flux. The main disadvantage of this technology is very long response time. We have to wait some time in order to get this current, and but still, here's the picture. Also, this detector, it looks like this. You have a small, a long cable where this detector sits, and you can put this pretty thin, small detector inside the nuclear reactor core. And one more application of neutron detectors at the nuclear reactor installations, and this detector is called a boron meter. You know that in water, in order to control the speed of the nuclear reaction, we add so-called boric acid, and boron effectively absorbs neutrons due different through the reaction, which I show you here, and by adding different amounts of boron, you can control the power of the nuclear reactor. But you have to measure this concentration with this boron acid, and this can be done with typical boron counters like this, and a neutron source. And this is made by using some auxiliary circuits which are located inside the nuclear power plant, and through these pipes is passing this water, which is dropped with this boric acid. And in order to calculate the concentration of this boric acid, because it's very important to, for example, to decrease the power of the nuclear reactor when it's necessary, it can be done, for example, by chemical methods. You can take some sample, measure it, and then get the concentration of this boric acid. But it requires time, and in some applications you have to do it online. And for these purposes, we use radiation detectors, which are called boron meters. We have a neutron source here, and two, for example, two or one proportional counters with boron 10. Yeah, and you have a source. And by measuring the number of counts of neutrons as boron inside this tube absorbs neutrons, you can calculate the concentration of this boron acid, and to immediately process the information and quickly control the nuclear reactor. The same reaction, we could burn 10, lithium 7 plus alpha particle, 2 proton recoils with energies 1 MeV and 1.8 in the middle. Let's move to some other applications of nuclear detectors in different processes related to nuclear power plants. For example, detectors are used in processes so-called decommissioning or decontamination. When the nuclear power plant stops operating due to some reasons, because, for example, it's now out of age, it's too old and requires to stop the operation of nuclear power plant. People start to decommission it, to remove all radioactive elements from the nuclear installations and to keep it clean. And in order to understand the level of radioactivity and understand what to deal with this partly including nuclear waste, we measure the activity with different detectors, for example, gamma spectrometers, and understand the level of the activity. When we decommission and demolish this facility, we can, before it, we can measure the level of this activity in different parts of nuclear power plants. And for example, some applications can be used, for example, to measure the nuclear waste. And we know the waste has some different grades, low radioactive, high radioactive, and the treatment of this material requires some segregation in order to safely store it in some specific facilities. And finally, when you close to a nuclear facility and know to make sure that it's safe, now you can do some final radiation survey and measure the levels of radioactivity which surrounds the place where the nuclear reactor used to be, or can be used further. Some nuclear also nuclear radiation detectors, which are located at the nuclear power plant. For example, all personnel that works at the nuclear reactor requires some specific procedures. For example, when people enter the territory of the nuclear power plants, which is so-called a territory with specific permission to get into, and this territory there are risks of radioactive materials. And these radioactive materials can be must be valued. You can use it with a conventional dosimeter. Personal, yes, this dosimeter goes to the nuclear power installation, works there. But despite that fact, all people coming back from the nuclear reactor, they pass through this so-called contamination monitors, which are also contain some examples ventilation detectors. They pass through this flamethrower, and this installation gives you the permission to pass through the and leave the building safely, to make sure that you don't have some contaminated materials on your clothes, on your body, and so on. Also, there are some installations inside the nuclear reactor, inside the nuclear power plant on the territory, which are called cut rules, radiological cut rules, where personnel measure some samples of different materials, and for example, from reactive coolant, ethylene, and other materials which can be potentially contaminated, in order to understand the potential values of these materials. There's a rule, different kinds of detectors, germanium detectors, scintillation detectors, in order to give understanding of possible contamination. That's all about nuclear instrumentations, and let's move to some other applications of detector technologies. I think you know many of them, but just who doesn't know, I can tell you that in the fields of medicine, which is called nuclear medicine, with radiation detectors, we use so-called nuclear imaging, and can get the image of functioning of people's organs using two popular techniques, which is called one positron emission tomography, and the second one is called single photon emission computed tomography. The first one, which is called PET, usually uses short-lived positron emitters like fluorine 18, for example, or oxygen 15, and the technique is based on the process which is called annihilation. In this case, in the patient is added a trace amount of radioactive material, for example, fluoride 16, which is connected to some biological substances, for example, glucose, which can, and this molecule is absorbed by, for example, cancer cells, which consume these radio tracers more extensively compared to normal cells. And this material stored in one place, and then positron emits. It finds one electron from the human atoms, and in this, when it happens, there are two photons with energy 0.5 MeV, which in some gives you two gamma ray photons, which are moving in opposite directions. And by having these installations, actually, this installation is a combination of scintillation detectors, different photomultiplier tubes, and for example, sodium iodide, which is used in these applications frequently. You can get, by rotating this thing, you can get the image of inside the points of this possible cancer, and then it can be identified and treated with different techniques, including radiation therapy. In single photon emission tomography, we use basically gamma emitters with energies from 100 electron volts, kiloelectron volts to 200 kiloelectron volts, specifically techniques of 99. The technique is similar to this, but in this case, you will get only one gamma ray, which can be detected by also a combination of scintillation detectors, photomultiplier tube, and for example, big sodium iodide crystal with thallium, and using a lead colorimeter, you can focus your gamma rays and get the image by rotating these detectors. You can get the image of, for example, blood flow in the body and understand whether there are some problems with blood circulation in the body of the patient. There's two techniques which use scintillation detectors. Now there are some also things to make, for example, small these neutron emission detectors, tomographs, in order to, for example, study pharmaceuticals in small animals and run needs to, for example, change photomultiplier tubes with silicon photomultipliers. One more application, which is widely used in different areas, in industries, in different industries, including oil and gas, mining, metal and steel production. And this is done by a simple technique, which is called non-conducting measurements. There are some experiments or facilities where it's impossible to measure, for example, the level of liquids or the density of some materials inside different well pipes or different vessels. And in order to do this, because the temperature, for example, can be about 400 degrees, or there are some corrosive materials that can destroy any simple device which can be placed inside this vessel. Other techniques, for example, acoustic measurements, you can put this device inside the vessel. And this, when this situation happens, you have to do so-called non-conductive measurement, and this is done very simple. You have pretty intense source, for example, gamma, copper 60 or cesium 137 isotope, and put it on one side of the vessel. And on the opposite side, you can place your detector. It can be the simplest organic scintillating detector with a photomultiplier tubes. For example, here's how it looks. The picture, this is the vessel. And by measuring counts of these gammas, you can understand the level of liquid inside this vessel. These techniques can be applied in, for example, you can put several gamma ray sources on one wall and a couple of detectors on the opposite side and measure this flux. And here it works the same equation about mass attenuation coefficients, which is used, which is followed by exponential absorption of gamma rays. Simple question, but we can apply it in different applications, including installation, where we can measure the density of materials inside this by this the same technique, the gamma ray source in the detector. And for example, you have conveyors when some sort of materials can be moving. You can measure the mass of this material by knowing the speed of this facility installations and the density which can be measured by installing, for example, here under this line. That's, for example, can be done to calculate mass of processed pulp or paper or some materials which are extracted from the earth. One more experimental approach to use this technique is to do so-called non-destructive testing, specifically for pipes. The idea is similar to the previous idea, which I explained in non-touching measurement. Here you can put an intense gamma ray, for example, iridium 132, and place the detector on the opposite side. And in these applications, we can use some sophisticated, for example, detectors, for example, silicon detectors, but still in this application, we can use simple films and see the image of the potential defects in welding by getting the image of this structure similar to medical imaging using X-rays. One more application, it's not practical, just to give you more details that our smoke detectors contain a radioactive isotope 241 aggressive, which is located inside this detector. And americium 241 is an alpha emitter, and this alpha emitter actually, this smoke detector actually is a small ionization chamber. We have an alpha source and measure in current mode the current passes through this ionization chamber. And when the smoke appears, you have less current in your installation, and then the signal, the siren is triggered, and you can feel that your somebody is smoking in the room. But now there is a tendency to replace this americium 241 detectors with other techniques, for example, using photo detectors, but it's still this type of detectors which are still produced. Application also of detectors can be done in so-called homeland security when you have to prevent, for example, nuclear material smuggling. You know that all treatment of nuclear materials is very strict. You have to follow some official typical procedures, and any signs or any attempts to steal, smuggle some material can be very hazardous for the country. And there are so-called portal monitors which are installed during near the nuclear facilities, which can trace by measuring different types of radiation, mostly gamma rays. They can tell you what is inside this container. Sometimes we have techniques when there are neutron source that strikes at this container, and you can get a response of gamma rays by using capture and measure the activity of nuclear materials inside this container. And slide that is actually not about radiation detection, but application of a photo detector, which is called a silicon photomultiplier, in everyday facilities. This silicon photomultiplier was originally used and tested in applications connected to radiation detectors as a replacement, a modern semiconductor replacement for photomultiplier tubes. But now there are lots of other applications, including so-called LiDAR techniques, laser detection for measuring the range and the distance between different objects. And this is frequently applied in self-driving cars. You can see the installation on the roof of this car. It contains these detectors, which actually contain inside a laser, which strikes the laser beam, and the detector, which is a silicon photomultiplier, and you have a transmitter and a material like this, or like here. And by measuring the distance and the time between these pulses, between these pulses, you can give and get the information about the distance in front of you, as it's in present example. Here is the example how it works. You have some sort of a start pulse, which is initiated by the laser. You have some optics in order to focus it, and you have target. You have a light which is moving towards this target, and then it reaches the target and reflects. Returns. After focusing this light, you will get the stop pulse. And by knowing the time between the stop pulse and the start pulse, you can measure the distance between your moving object and the object which is in front of you, behind you, from different sides. And by using this, you can understand about, for example, emergency braking of this car or something like this. It's only used in other applications, in aerial applications with this LiDAR technologies, using, for example, radar or sonar technologies where ultrasound is used. When you combine all these technologies, you can get a better picture of objects surrounding you. And actually, my last, almost last slide for today, I would like to underline that the whole topic of radiation detectors is devoted to fundamental physics. We only covered some basics of how typical simple detectors use. But if we combine several types of detectors, or if we build them bigger or increase, unite some of them, we can get these big installations, like, for example, Atlas detector is located in Switzerland, in Center for Nuclear Research in Geneva, and you can see that the size of these installations can reach, for example, 40 meters in length and up to 30 meters in height. Massive constructions, mostly to study nature, understanding of how our universe was created, for example, by studying different particles. If we, for example, collide protons at targets, we can understand, we can give rise to new particles, and by studying them, we can get some fundamental information which is concerning our universe. And there is energy physics, astrophysics. We can use detectors on the orbit, on satellites, to understand gamma rays, for example, cosmic rays, that we construct laboratories in the mountains, like in Bolivia, and study cosmic rays, and all we use. But all work which we do to study this phenomena, we use radiation detector, different types of them. For example, here's sophisticated detector bolometer for measuring and searching for so-called neutrinos beta decay, And there are lots of experiments all around the world which utilize the power of radiation detectors to answer questions about the nature. And actually, this is my last slide. I put here some books which I used to prepare my presentations. Here you can see them, and if you are interested in the subject, you can find them. They are available on the internet, and use them to deep into more details how to detect different particles. I think that's the end of my lectures. Thank you for your attention. Have questions? I can answer them. If you don't, you can answer. Ask me later. Okay, thank you.
Thank you very much for your attendance. I will explain in Spanish. Ya hemos terminado con todas las lecturas, entonces ya estamos listos para poder rendir el examen. Como se les había mencionado, el examen va a durar 1 hora. Los que están presentes, les pido que por favor, vamos a tomar 10 minutos para poder alistarnos y vamos a pasar a la biblioteca que está justo a la entrada, y ahí se les va a tomar la tercera asistencia. Para los que están virtual, tienen 10 minutos para poder alistar sus cámaras, porque se les ha solicitado que tengan las cámaras prendidas en todo el momento del examen. Se les va a controlar y vigilar, y en aproximadamente 10 minutos ya se les va a mandar el enlace, así que por favor, los presentes pueden ir pasando a la biblioteca. Y los que están en la reunión virtual, vamos a empezar a prender sus cámaras. Después de ese evento, nosotros ya les pedimos a los que están presentes virtualmente que nos acompañen al evento de clausura. Va a haber una presentación de las oportunidades que tienen en la Universidad de México después del examen, y luego ya el evento de clausura va a ser máximo unos 10 a 15 minutos y vamos a terminar con las fotos. Les agradezco mucho por su atención y éxito en su examen.